Earthquakes around the world are concentrated mostly along the boundaries of tectonic plates. The largest earthquakes occur along plate boundaries called subduction zones, like the one offshore of Japan. Here, the Pacific plate moves westward towards Japan at a rate of 9 centimeters per year. A cross-section through this region reveals the structure of the subduction system, showing the Pacific plate descending underneath an overriding plate on which Japan sits. The plates are made of elastic rock, and the asthenosphere beneath them consists of rocks that exhibit elastic behavior at high strain rates while flowing viscously at low strain rates. Over geological timescales, the subducting plate gradually sinks into the asthenosphere. To see how earthquakes fit into this picture, we zoom in on the region around the plate contact, and we also slow down our clock to focus on processes occurring over much shorter timescales. When we do this, we can recognize 4 distinct stages of earthquake cycle deformation. We start in the time period before a major earthquake, called the pre- or interseismic stage. This interval lasts several decades to centuries to even millennia in some cases. During the interseismic stage, a large part of the plate contact is locked by friction. The subducting plate continues to move at several centimeters a year, causing the overriding plate to deform and stresses to build up around the locked interface. The earthquake happens at 12 on our clock. At this point, stresses become so high that the plate contact breaks, and the 2 plates slip rapidly past each other. This rapid slip produces seismic waves that propagate away from the fault and may cause damage in the region nearby. After the earthquake is over, the overriding plate is stretched seaward relative to its pre-earthquake position, with uplift near the subduction trench and subsidence near the shore. This vertical motion of the seafloor may also generate a tsunami, as the water column is abruptly raised and then falls to the sides. Let's see the earthquake again, but now focusing specifically on the deformation within the Earth. The regular grid here represents the state of the subduction system immediately before the earthquake. As you saw earlier, the overriding plate slides over the subducting plate during the earthquake, perturbing the grid. The third stage of the earthquake cycle starts soon after the event, when 2 things happen. First, the plate interface relocks. From this point onward, the subduction zone begins building towards the next earthquake. Second, the deeper part of the subducting plate continues to slide into the Earth past the asthenosphere beneath the overriding plate. This is commonly referred to as afterslip. During the 4th and final stage of the cycle, stresses produced by the earthquake in the viscous asthenosphere decay away. This post-seismic relaxation phase lasts several decades for the largest events. Once post-seismic relaxation has ended, we have returned to the interseismic stage, in which the deformation reflects only the slow plate motion across a locked part of the plate interface. We refer to the earthquake cycle as the repeating sequence of these stages before, during, and after a major earthquake, although we recognize that the cycle duration varies significantly from one earthquake to the next. Satellite geodetic networks allow Earth scientists to measure the minute motion of the Earth's crust and provide key constraints on earthquake cycle deformation. Through these careful observations and models of the subduction system, a great deal has thus been learned about the earthquake cycle.